All right, so this is the first video you're watching of this lesson. It's about the 10th that I've shot this morning. I'm really trying to figure out how to approach sections 4.6, 4.7. So 4.6 is non-homogeneous equations. 4.7 are forced oscillations. That's the application. 4.8, I'm definitely going to skip. Systems of differential equations are super interesting, but we've kind of covered those already. I'm not sure if I'm going to cover them again from a different perspective. And then the Laplace transform, which is something that always gives students trouble, which is 4 point, is it 4.12 and 4.13. Now, from my perspective, if we were able to cover this well this week and next week, we have 2 weeks of classes left, I think. Yeah, just 2 weeks, and then it's finals. So I'm kind of inclined to focus just on this. Hold on, I got to pause for a quick second. All right, am I back on? I am back on. So I think this is all we're going to do for the next 2 weeks, and it's plenty. And part of the reason it's plenty is I recognize in trying to make these videos, which I want to have for people to refer back to, even in addition to the Zoom recordings, is that these are the sorts of lectures that I pause a lot. I put an idea, I put a calculation on the board, and I turn to you and I check in. There's lots of steps here, and it's not so much that that it's difficult conceptually, say like chapter 3, but there are a lot of pieces and a lot of paths to take. You have to make a lot of choices, make a lot of decisions, and it's nice to be able to interact with people, and hopefully our Zoom recordings will do that. So to kind of start off a little bit, sections 4.1 through 4.5 deal with homogeneous equations. Now, a homogeneous equation in 4.5 was this very general damped harmonic oscillator. And there's a circuit analogy to this too, right? This would be, let's see if I can just write it down, possibly. Right, so we'd have something like, I don't know, and then this would be 1 over LCQ. I think it'd be something like this, because the spring is like the capacitor, the damping force comes from the resistor, and then the inertial term is like the inductor. And so whether it's a damped, it's a mass and a spring, and there's friction within the spring, or it's inside of a viscous fluid, or whatever. But these damped equations are still homogeneous. There's nothing driving the system. There's nothing else going on. The moment we put something into the system, for a circuit, that would be some sort of maybe time varying voltage. It could be a motor or a spring of some sort, a wound spring inside of a pendulum. It could be that the mass spring damping system here is going over some surface, and that this surface represents input, right? If this is a rigid rod on a wheel, then, and if this surface is moving, or if conversely the structure is moving, then this is going to create an upward force. This bump here is going to force this mass up and compress the spring, regardless of whatever natural motion the system would undergo. Or it could be that there's some apparatus, and this looks kind of, like a bumpy road, but it could also be that you have some machine that's on a floor, and on a factory floor, and there are vibrations traveling through that floor. And this is just an exaggeration of the floor flexing ever so much, which is creating input into the machine itself, which can then oscillate in a damped way. So the 0 here is about to go away. What 4.6 begins, and 4.7 explains why, is having some function, some input. So 4.6 is about this equation, and this is the input into our system. And 4.6 is actually only about some special cases. This is the case where f is a polynomial. That includes a constant. It could be sine, it could be cosine, it could be an exponential plus or minus at. It could be a polynomial times an exponential, etc. There's special functions. They're all the functions that could be in the kernel of L. Now, the 4.6 is more general than we're going to deal with. We're going to deal with a smaller bit of it. And 4.6 leads right into 4.7. And so I'd kind of like to talk about that a little bit, just very briefly, before having a separate video on 4.7. So, maybe just really, really lightly. What 4.7 is about is resonance. And it's the idea, you've experienced this if you've ridden a swing or you pushed somebody on a swing before. Sort of intuitively, either through pumping your own legs if you're swinging by yourself, or if you're pushing somebody, right? So you've got somebody is on a swing or whatever, and you're back here giving them a push. When they come up, you wait until they reach peak motion, right? And then you give them an impulse. It might last for a half a second or a second, right? You place your hands on their back and you shove them off, and then they go maybe a little higher. Then they come back and you wait, and you push them at the peak of their motion. You wouldn't push them down here, right? Because then you would impede. You would be injecting energy into the system before it reaches maximum amplitude. You time it just right. And it's the same with pumping your legs. If you pump your legs out of phase with where you are on the swing, it doesn't drive the motion. And when I say drive the motion, what I mean is, right, the goal on a swing is very simple. You start sitting on the swing with no displacement and no velocity. Maybe you back up a little bit to give yourself an initial displacement. And then, but the thing is, if you didn't do anything, and if the bearings up here where the chains mount, if you didn't do anything, you would expect a very boring swing, right? You wouldn't swing very much. So using your legs, you drive the motion. As you start to swing, right, you kick your legs to achieve a larger displacement, right? And then you tuck them back, and you're trying to drive this motion to a certain extent, right? And then you get to the point where, you're starting to have fun. You're driving this motion. Or, if you're an older sibling or an uncle, an aunt, or if you're helping out some other person by pushing them on the swing, then you're injecting, right, a force at these times to increase the amplitude of oscillation. You are the FT. Now, what you're doing with, if you're pushing someone on a swing, it's kind of discrete. It's very likely that you're basically just putting in small bits of impulse periodically, right? Depending on when they come back. They come back, and you put your hand on it and you push. If you're kicking, it's probably something a bit more sinusoidal, or at least might look sinusoidal, where there's some amount of energy, then you're tucking the leg, there's some amount more, and I don't know exactly how that looks, but you have some other force that's doing it. So this is what's going on. If you do this with the right frequency, the motion gets larger. If you did something out of phase or herky-jerky with your legs, it wouldn't drive the motion. It would make some really kind of irregular pattern. It wouldn't get bigger. You know this from experience. If you don't pump your legs right, you don't swing higher. And you can probably imagine that if you randomly applied forces to somebody on a swing, it wouldn't drive the motion either. If you push them a little lower on, or if you grab their feet when they're trying to return, it's all sorts of things you'll do that will decrease their amplitude, or at least not let their amplitude increase. So that's the basic idea of resonance, is not just having an input, but having an input of the right frequency to match the natural motion of the system, but to inject energy at just the right time to cause bigger and bigger amplitudes. So that's where we're going. How do we get there? Well, let's start with this. And let's imagine that this is an nth order linear differential operator with constant coefficients. All right. The solution to this is going to be made of two pieces, an x sub h and an x sub p. And this is the homogeneous solution. This is what we've been doing 4.1 to 4.4. And this is the particular solution. Now the word particular gets used in a couple ways in this book. And so, right, if you apply your initial conditions, you get a particular solution instead of a general solution. That's not what this is. This is the other part of the solution for a non-homogeneous differential equation. Now what happens when I plug in x? Well, this is L on x sub h plus x sub p. This is a linear transformation, so I can distribute it over the sum. And by definition, the homogeneous solution equals 0. So you might ask, why do we even need this? This is not a homogeneous equation. So let's go back physically to what's happening. If I'm talking about a damped harmonic oscillator system, there's a natural motion in the absence of any external force. The solution to the homogeneous equation is what this thing does anyway. Now I'm going to interact with it. So I'm going to modify what it does anyway with what I'm doing to it. So that's why we need the homogeneous equation. It captures something essential about the system in the absence of input. And also, this is going to have all of our constants of integration. So if this is an nth order linear differential equation, there are n undetermined constants. Thinking back about the linear algebra, this is formed, this is formed from the basis of the kernel of L. This is a linear combination of the kernel of L. To figure out all those values, we would need n initial conditions or boundary conditions. We need more information. What's happening specifically to determine those? And then what's this? Well, this is going to tell us how to modify the behavior of our system given the input. This is the thing that's going to equal our f of t. And this is going to be quite specific, meaning that there's no undetermined coefficient here. It's not going to be a cn or a cn plus 1 or a b or a d or anything. All the numbers, all the parts of this will be explicit because we won't have enough information to figure out another constant anyway. All right. So let's go ahead and find some particular solutions. Here's the idea. We'll start with the first order equation. If I have something like this, well, that's d plus 3 on x equals e to the t, right? Now, I know that the homogeneous solution is a e to the minus 3t. How do I get something for the particular solution? Well, here's the idea. One way to justify what I'm about to write here is to imagine that you operate on both sides with another differential operator, call it m. And the goal is to make this into a homogeneous equation. So imagine I do d minus 1 on both sides. I'm multiplying both sides by d minus 1. What would that do? Well, it would equal 0 because e to the t is in the kernel of d minus 1. If I were solving this equation, and I'm not, but if I was, I would know that I get my e to the minus 3t from here, and I get an e to the t from here. So this inspires me. If this second order equation has these two solutions, then maybe I'll try the e to the t up here. Now this is not something you're going to have to do regularly. I'm just trying to justify why I'm going to say, well, maybe e to the t is my particular solution. But it might not be 1 times e to the t. So I have to figure out what the coefficient is. How do I figure that out? I plug it back in. So I'm going to have x prime, which is a e to the t, plus 3a e to the t equals question mark e to the t. And so this is 4a e to the t equals question mark e to the t, which is true if a equals 1/4. So this is my particular solution then, is 1/4 e to the t. And then my general solution is going to be my homogeneous a e to the minus 3t plus 1/4 e to the t. So here's my x of h, here's my x of p. We're going to do a couple more examples. Now, this can actually get a bit more complicated if my input is similar to the homogeneous equation. So suppose my input is e to the minus 3t. So I have my d plus 3, x equals my e to the minus 3t. Now I have a problem because I know that my homogeneous equation is a e to the minus 3t. And using what I just did, I might want to guess that my particular is e to the minus 3t, but I can't. I've already used that function up. If I try to use this function again, everything will collapse. I won't have a particular solution. So thinking again about that technique, what would I multiply both sides by to turn this into a homogeneous equation? I would need another factor of d plus 3. So I'm using this to justify my guess. Why is this 0? E to the minus 3t is in the kernel of d plus 3. So if this were the differential equation that I were trying to solve, well, this uses the techniques of 4.3. I'd have a repeated root. I'd have x equals e to the minus 3t and t e to the minus 3t. So maybe this is my guess. And again, I don't know if it's 1 a to the 3t, so I should put a constant there. How do I find the constant? I plug it back in. Now you can see very quickly this becomes a little onerous, right? I'm going to have a product rule. And so it doesn't take very long before these become quite a bit of work. I'm going to try to be, whoops, I forgot a constant here. And I'm struggling sort of how to figure out how to best do this online. All right. So I do this out. I'll have an a e to the minus 3t. This is a product rule. And we're going to get some cancellation here. So these will cancel. And in this case, a equals 1. So my particular solution then is just t e to the minus 3t. Notice that we found out what a equals. Be careful, this isn't the particular solution. We found out what a equals, and we have to go back to our initial guess, a t e to the minus 3t. Okay. So then my full solution is my homogeneous plus my particular. So things become more complicated if the input is a function in the kernel of the operator. We'll have to put on another value of t. All right. So let's do a little higher order example. Suppose I have something like x double prime plus x prime minus 6x equals e to the t. So this is d squared plus d minus 6 on x equals e to the t. This factors into d plus 3, d minus 2, x equals e to the t. So this isn't going to be too bad of a problem because this is not in the kernel of either of these. That's when things become a bit more problematic. We need to start putting on t's. My homogeneous solution is a e to the minus 3t plus b e to the 2t. And my particular solution is going to be some multiple of a e to the t. How do I find that out? I have to plug it back in. Right. So let's do that. I'll have two derivatives of this. Well, that's just the same. Plus one derivative of it, which is just the same, minus 6 times just the function, equals question mark e to the t. So that's 2 minus 6 is minus 4a e to the t equals e to the t. And so a equals minus 1/4. So then my particular solution is negative 1/4 e to the t. And my whole solution is my homogeneous solution plus my particular solution. Right. So those are some basics. Maybe just one more here. What if we had x double prime minus x prime equaled, I don't know, equaled 3? Well, this is d squared minus d on x equals 3. This is d times d minus 1, x equals 3. 3 is in the kernel of d, so my homogeneous solution is a constant plus a constant times e to the t, and my particular solution can't be a constant. It'll have to be some power of t, some multiple of t, so like ct, for example, could work. How do I figure it out what the constant is? I plug it back in. Two derivatives of that is 0 minus c equals 3, tells me the value of c. So this is 3t. So my full solution is a plus b e to the t plus 3t. Now, if you look on, what is it, page 161, there's kind of an intimidating table of what the particular solutions are. It's not so intimidating as Theorem 28, and that's because these are general results. This allows us to look at real general inputs into our differential equations. And I think I'll deal with that in the next video. One way we can do this without getting really carried away with algebra is suppose I had something like this, and the what are the I had 3t minus 1. This is in the kernel of this. So our particular solution is going to have to be a quadratic. But putting a quadratic through all of this would be a nightmare. But it would be sufficient to just match this. You could imagine a list of differential operators and then a list of particular solutions, and just being able to say, this is the one I would have to try. I'm not going to, but just matching up what they are. Because the rest is just algebra. It's just churning through all the derivatives to find out what these are. And then generally you end up with a system of 3 equations and 3 unknowns equating coefficients. It's a bit of a nightmare, even in the simplest of cases. Now, so that's probably something I'll do in a follow-up video. So I'll stop this video here.